Our first example today, as we delve into chapter 3, is the experiment of rolling one fair six-sided die once. Roll a fair six-sided die. And to let our random variable, capital X, be whatever you get, the outcome. A 1, a 2, a 3, a 4, a 5, or a 6. Should we think of this in terms of sample spaces? Well, we could. We've done that before. Do we have to think of it in terms of sample spaces? No. We can think of it in terms of this new idea of a discrete random variable. This is a discrete random variable. I will always abbreviate RV, with a corresponding distribution Our book calls this a PDF for probability density function, but again, our book is 20 years old. In more recent years, if you look up books on probability theory, they will more typically call this a probability mass function. Probability mass function, or PMF. And I do think that's better terminology. Okay, here's why it's better terminology in a nutshell. With discrete random variables, the PMF, the probability mass function, actually computes probabilities for you. Probability masses, so to speak. In chapter 4, with continuous random variables, we will have a PDF. We'll still use little f of x for it. But when you plug in numbers into the PDF, you don't get probabilities. You get probability densities, which we will ultimately see means you have to integrate PDFs to find actual probabilities. It is quite analogous in physics to, say, you got on a number line, point masses, individual point masses that you can, for example, find the center of mass for, versus, say, a thin rod that's got a density function, a mass per unit length, that you have to integrate to find the mass or center of mass for. Calc 2 kind of stuff. You should have learned about that kind of stuff in Calc 2. It is very much analogous to that. What's the probability mass function going to be in this case? Well, if it's a fair six-sided die, each side has the same likelihood of occurring, 1/6. This is going to give the probability that capital X equals little x. Don't get confused by two equals in here like this. Does f of x equal p parenthesis x and that equal little x and parenthesis? No. These are two distinct quantities, f of x and p of capital X equals little x. The value of f of x at the input little x is the probability that the random variable equals that value little x. Capital X is kind of like an abstract thing, an idea, so to speak. Now, what is a random variable really? If you want to be extra technical about it, like grad school level stuff, it's actually a function, but I'm not going to get into that. Little x is a number, but it's an arbitrary number. So it's, in a sense, also a variable. But what does this equal? It equals 1/6 if little x is 1 or 2 or 3 or 4 or 5 or 6. And equals 0 elsewhere? Yes. We do technically, for some technical reasons, want this to be defined for all x. It's going to equal 1/6 for 6 values of x. If little x is 1, 2, 3, 4, 5, or 6, and it's going to equal 0 elsewhere for all other values of x. I like to abbreviate this OW for otherwise. Sometimes I say elsewhere or for other x. So really, we're defining this probability mass function, this PMF, for all values of x, for all real values of x. And so if we were to graph this function, I was just talking about this in my Calc 1 class yesterday, it would be a graph that's got some removable discontinuities that with my Calc class yesterday, I was saying these are kind of like dumb removable discontinuities because there's holes, there's points missing from the graph, but their points are elsewhere, so to speak. The graph would be mostly the horizontal axis, except exactly 1, exactly 2, exactly 3, 4, 5, and 6, where the output at those numbers is 1/6. But elsewhere, it's 0. And I think when I taught Calc 1 yesterday and talked about these as kind of like dumb removable discontinuities, I was mentioning some applications, and I was thinking of physics applications, but here's an application of dumb discontinuities. Well, in this case, they're actually not so dumb. They're important. Okay, this graph represents the probability mass function in this context. And yes, you've got 6 removable discontinuities where the limit as x approaches any one of these numbers is 0, but the function value is 1/6. But to tell you the truth, they're not dumb here. They're essential. This is what's going on. This is what the model is about. I did forget last time, or I ran out of time to talk about CDFs, cumulative distribution functions, the capital F that you encountered in the reading and the homework. Let's talk about that now. Capital F of little x. In both chapters 3 and 4, I will call this a cumulative distribution function. Cumulative distribution function. CDF for short. CDF. Some people even shorten these names further, and they'll just call little f a probability function, and they'll call capital F a distribution function. Well, I think it is good to emphasize the word mass here to distinguish it from a density in chapter 4, and the word cumulative, because it is accumulating probabilities, in a sense. It's the probability that your random variable, capital X, is less than or equal to the given number, little x. And we can also define this for all values of x as well. Word of warning, back up here, this equality is because the random variable is capital X is discrete. That equality right there is not going to work in chapter 4 with continuous random variables. Again, I already mentioned that 6 minutes ago. The PDF probability density function in chapter 4, when you plug in numbers, doesn't give you probabilities. You have to integrate it to get probabilities. Here, because x is discrete, little f of x is an actual probability. It is a positive number in this case when x is one of these 6 numbers. And is never negative. It's always greater than or equal to 0. You can't get negative probabilities. And it can't be bigger than 1. All the probability laws from chapter 2 are still going to hold. This equation is true no matter what, even with continuous random variables. Even in chapter 4 with continuous random variables. CDFs, capital F of x, always equals that probability. Always, always, always. You might wonder, are discrete random variables and continuous random variables all there is for random variables? The answer is no. There are mixed random variables that are both discrete and continuous. How is that possible? I'll probably find time to talk about one example sometime, but not today. What does this equal? Evidently, I have to use the PMF, effectively add up its values. Yeah. In the discrete case, this equation is only going to work since x is discrete. And it's also only going to work because it's taking on whole number values with positive probabilities. I have to be a little bit more careful if it was not the case. And taking on only whole number values, integer values with positive probabilities. Okay, and I could write what I'm about to write a little bit more generally, but for the sake of this example, I'll just write what it is. It's the sum of the values of little f for this example. I'm going to call the input of little f for the summation t. And I'm going to go ahead and just let t start at, should I start it at 1 or 0? I'll start it at 1. And do I go up to x? Well, you saw it in the reading. Technically, we should go to the greatest integer in x, which I write like that. I think the book writes it more like this in the book. Okay, I could write this summation a little bit more generally. I could actually start t at 0 or even -1 or -2, or sort of think of this for all t as being less than or equal to that. I mean, it's a little funny with summations because you're implicitly assuming with the summation that t keeps going up by 1 each time. And so it's a little funny. It's not a real big deal. The key thing is we're adding up values of little f. What is the greatest integer in x? Well, if x is a whole number, the greatest integer in x is that whole number itself. If x is an integer, the greatest integer in x is x itself. If x is not an integer, like 4.5, or let's try 4.1, if x is 4.1, the greatest integer in 4.1 is 4. That's the greatest integer less than 4.1. Greatest integer in 4.1. If x is 4.9, the greatest integer in 4.9 is also 4. That's the greatest integer that's still less than 4.9. Once you get to 5, the greatest integer in 5 is 5. Greatest integer, I should have said less than or equal to 5. So effectively, I mean, in this example, we would imagine mostly plugging in whole number values for x like 1, 2, 3, 4, 5, or 6. But what doing this allows us to do is it allows us to think of this CDF as being defined, once again, for all x. It doesn't quite match t starting at 1, but effectively, the graph of the CDF is defined for all values of x. And it has jump discontinuities at, in this example, these whole number values 1 through 6. It's 0 when x is less than 1. At 1, it jumps up to 1/6 because the probability of being capital X being less than or equal to 1 is the same as the probability of x equaling 1 for this example. It technically stays at 1/6 until you get to 2, but when it jumps up to 2/6, 1/3. What's the probability that when I roll a die, I get less than or equal to 1.9? It's the same as the probability of getting less than or equal to 1, which is the same as the probability of getting a 1, which is 1/6. Because I can't get 1.9. It turns out, for the making the theory all work nicest together, to think of this as being defined for all x. And it keeps jumping up by 1/6 of a unit. Here it would be at 1/2. Every time you get to the next whole number. It's up to 4, it would be up to 2/3. And here, when we get to 5, it would jump up to 5/6. And when we get to 6, it would jump up to 1. And stay at 1 thereafter for all values of x bigger than 6. So technically speaking, the CDF is defined for all x, and it's in the discrete case, it's going to be a step function with jump discontinuities. In this example, the jumps all have the same size, 1/6. They go up 1/6, but in general, they don't have to be the same size. This distribution has a name. This kind of distribution, it's called a uniform distribution. Hey, because these outputs are all uniform. They're all the same number, 1/6, at these 6 discrete values of x. This is called a uniform distribution. You can generalize this to a general uniform distribution that's got n discrete values at which the probabilities are 1/n. Does that make sense? Did you catch what I said? N discrete values at which the probabilities are 1/n. Like if n is 100, there's 100 discrete values at which the probability is 1/100. And obviously, the sum of all the PMF values is 1. We can write the sum of the little f of x values is 1. I could write in general all x here, though in this example, x really goes from 1 to 6. That's equivalent for this example. For this example, to writing the sum of the values of little f of x as x varies from 1 to 6 is 1. Okay. All right. What else did we talk about the other day? How about the mean, the variance, and the standard deviation? For this example still, what would make sense for the mean? How about something right in the middle? 3.5? What would that be? 7/2? That seems like that should be the mean, shouldn't it? It's like a center of mass. Yeah, the formula for the mean can be thought of as the same as the formula for a center of mass. When your total mass is 1. When you add up all these point masses that have a mass of 1/6, you get a total mass of 1. It's like physics. Like that's the balance point for your seesaw, or teeter-totter if you prefer. What's the mean? Mu. Also called the expected value of x. We use both notations. You should be completely comfortable with both notations and realize these are always the same thing. Mu equals e of x. Mu, the mean, equals the expected value of x, always, for the given random variable. I mean, sometimes we might put a subscript on the mu to emphasize what the random variable is. Should I do that? I won't bother, but sometimes we will. What does it equal? In general, it's a sum over all x of x times the PMF. For this example, that becomes a sum x goes from 1 to 6 of x times 1/6. You can factor out the 1/6 and write it this way. And obviously, you can certainly add up the first 6 numbers. You should maybe remember from calculus 2, maybe, or maybe discrete math, that the sum of the first n numbers in general is n times n plus 1 over 2, the first n positive integers. That's what we got here, the first 6 positive integers. N is 6. This is n times n plus 1 over 2. Oh, 6 is canceled, 7 halves. The sum is 42 over 2 is 21. 21 times 1/6 is 3.5. Just like I guessed a minute ago. That's the mean is a measure of central tendency. And since the distribution is uniform, these probabilities are uniformly spread across these 6 numbers that are equally spaced. It makes sense that the mean is right there in the middle. Now, the mean is not a particular value of x that it can take on with a positive probability. How do you interpret this mean? You interpret it as the theoretical long-run average. Take a die, a fair die, roll it, record the outcome, and then do that hundreds of thousands and maybe even millions of times and take the average outcome. It should be very close to 3.5. Now, will it be 3.5? Probably not exactly. Certainly will not be exactly with just one roll of the die. All right, this is analogous to our first class period where we were doing the coin simulation and seeing the graph approach 0.5 for the probability of heads. I'll call that the law of large numbers. That's kind of something similar going on here with the mean. What about the variance? The variance is a theoretical measure of spread that's harder to interpret than the standard deviation, but is sort of easier to work with abstractly because you don't have to worry about the square roots. The definition of the variance is an expected value as well, but not of x. It's an expected value of really a different random variable. X minus u quantity squared. Now, x is a random variable. X minus its mean is another random variable. Right? If the values that x can take on are 1, 2, 3, 4, 5, and 6, and turns out with equal probability so that the mean is 3.5, then the values that x minus mu could take on would be 1 minus 3.5, negative 2.5, 2 minus 3.5, negative 1.5, negative 0.5, positive 0.5, positive 1.5, positive 2.5 would be the 6 values that x minus mu could take on for this example, and they would have equal probability. Square those numbers. You know, negative 2.5 and positive 2.5 both have a square equal to 6.25. Negative 1.5 and positive 1.5 both have a square equal to 2.25. And negative 0.5 and positive 0.5 both have a square equal to 0.25. This random variable, for our example, can take on these 3 values and none others. And the probability of each of those would be 1/3, right? 2 times 1/6. This would have a uniform distribution as well. What should its mean be? Should be the average of those three numbers. I'm guessing the answer ahead of time here. We'll see if we're right here. Add them up, divide by 3. The average is 2.916 repeating. Is that really what we're going to get here? I'll have to wait and see. There's a theorem that gives what's called the computational formula for the variance. Expected value of x squared minus the expected value of x squared. And those are, again, different things. And the only time you ever get 0 here when you subtract them is if x is a constant random variable taking on one value with probability 1. And every other value has probability 0. That's a constant random variable. It's not really random, but we can think of it as random if we want still. Otherwise, you're going to get a positive quantity here. The expected value of x squared in general is always bigger than, except in the case of constant random variables, the expected value of x quantity squared. It's actually a fairly important fact that's easy to derive from this because that's never negative. It's called Jensen's inequality and has some applications beyond probability and statistics. But what's this? Well, okay, we could think of it this way again. We could take the possible values of x and square them. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. 6 squared is 36. What's the average of those numbers? It's 15.16 repeating. That looks like that's going to be what the expected value of x squared is. In general, this expected value is the sum over all x of x squared times the PMF values. Which for our example, whoops, for our example is going to be the sum x goes from 1 to 6 of x squared times 1/6. Yeah, that'll be 1/6 times what I just said. 1 plus 4 plus 9 plus 16 plus 25 plus 36. If I plug those in my calculator right, that was 91 over 6. That's 15.16 repeating. 15 1/6. So using this formula now, looks like we get 91 over 6 minus 7/2 squared. 7/2 was the mean. 7/2 squared is 49 over 4. Get a common denominator of 12. We'll get 182 minus 147 over 12. Hope I didn't make a mistake. That'll be 35 over 12. I think this is right. Lo and behold, 35 over 12, 2.916 repeating. Just like I guessed, right? Didn't I guess that? That was the average of 0.25, 2.25, and 6.25. You can generalize this to an arbitrary uniform distribution. There's a handy-dandy table in chapter 3 that I'm going to let you use. I'll give you a printout of it on exams. It's on page 78. Second option, name uniform. Density, really mass, 1 over n. These are the values of little f of x when x takes on these n values. These x's that you see have subscripts. The subscripts are integers, but the x's themselves don't have to be integers. They were for the dice rolling example. skip this moment generating function thing. The mean is the sum of the xi's divided by n. It's an arithmetic average, like you may have learned about when you learned about stats in your past. The mean for a uniform random variable, discrete random variable, is the same as the arithmetic average, sometimes labeled X bar in statistics. Almost always labeled X bar in statistics. And there's the variance. That's the expected value of x squared. Dividing by n means is the same as multiplying each of those xi's by 1 over n. Minus the expected value of x quantity squared. Can this be simplified? Yeah, but they're not bothering to. You could square this out and get a common factor of n squared. The author's just not bothering to simplify this. Can I clarify anything? You also learned about something else in your reading. Well, lots of other things. Properties of expected values and variance. The expected values, ones I mentioned last time. You also learned about a mysterious kind of thing called the moment generating function. Moment generating function. MGF for short. We have PMFs, CDFs, MGFs. In chapter 4, we'll have PDFs. Yes, in chapter 3 in the book, it's called PDF. Moment generating function for a given random variable x, m sub x of t, here we are emphasizing the name of the random variable, is also an expected value of something really weird, e raised to the t times capital X power. X is a random variable. If t is fixed, if t is a fixed number, then t times x would be a random variable. And e to the tx would be a random variable. For any fixed t, this is a random variable, and I can find its expected value and call that mx of t. But hey, that's kind of like function notation. Is t really a fixed number, or is it a variable? When you think about calculating this, do you think of it as fixed? But then you say, hey, my answer depends on t, so in the end, this is a function of t. Okay, well, this is weird. Who would care about moment generating functions? It would be a sum over all x. You always put whatever's inside the square brackets here times the little f of x. I hope that pattern has become clear by now. Except you use the lowercase x now here. Distinction between uppercase and lowercase gets important here in conceptualizing all this and not misunderstanding it.
So the first one's t is big X, the second is t.
These are big X's, that's a lowercase x's there, yep. Big X, capital X is the random variable, an abstract idea. Yes, in grad school math, it's a function. You can forget that I ever said that. Little x, you think of as an honest to goodness number, not really a random variable. An ordinary variable, maybe you might call it. Yeah, whatever goes there, you put it there, except you change the random variable to a number. Change the capital X to a lowercase x, and it gets multiplied by the PMF. And you do summations like this for these expected values for discrete random variables. With continuous random variables, these summations are going to become integrals, like magic. Is it really magic? No, it just feels like it. Poof, the sum turns into an integral. Remember that from Calc 2, right? The Riemann sum, poof, turns into an integral like magic. Is it really magic? No. It's really, in a sense, a definition, though the definition needs to be justified. It's not really magic. Just feels like magic, and it's fun to pretend it's magic, but not really. So for our example here, coming back to the dice rolling example, it would be this sum. Oops. E to the tx times 1/6, which you can actually write out as first 1/6 e to the t plus 1/6 e to the 2t, right? X is changing. I'm putting the x in front of the t instead of after the t when I do this. 1/6 e to the 3t, 1/6 e to the 4t, plus 1/6 e to the 5t, plus 1/6 e to the 6t. This is the moment generating function for the dice rolling example. Here's the amazing thing about moment generating functions. They generate moments. What's a moment? Well, the mean, the expected value of x, is called the first moment. The expected value of x squared that it's in the computational formula for the variance is called the second moment. The expected value of x cubed is called the third moment. The expected value of x to the fourth power is called the fourth moment. The expected value of x to the fifth is called the fifth moment, blah, 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 blah. And there's a theorem. Why are those called moments? It's a physics thing. Moment of inertia. It's like maybe related to that. You can look it up. I don't know. You could ask, why are they called moments of inertia in physics? I mean, is it related to time? It doesn't seem to be, from my understanding. The kth moment of x, this entire expected value is called the kth moment of x, where k is a positive integer, 1, 2, 3, 4, 5, 6, etc. It's a theorem that this is the derivative of the moment generating function, the kth derivative, evaluated at t equals 0. The book writes that like this: d dt with k's, that stands for kth derivative, of the moment generating function mx of t, do that derivative and then evaluate it at t equals 0. I'm putting an extra set of parentheses that the book doesn't put in there, but it's okay. You might also see people write this in an alternative notation that's a little quicker to write. M sub k with a k, M sub x with a k inside parentheses up there and then a 0 here would be an alternative notation for kth derivative evaluated at 0. But realize it is important to do the derivatives first and only plug in 0 at the very end, right? Don't plug in 0 too early. That would be a calculus 1 kind of mistake. So what about our example here? There's our moment generating function. What's its first derivative? Mx prime of t. Got a bunch of exponentials. And with the last 5 of them, I'm going to have to use the chain rule. The derivative of that one is itself. The derivative of this one is going to be itself times an extra factor of 2. To give me 2/6 or 1/3, I'll write it as a 2/6. This one I'll write as a 3/6. Then 4/6. Then 5/6. Then 6/6, which is of course 1, but there you go. Now plug in 0, and lo and behold, we get 1 plus 2 plus 3 plus 4 plus 5 plus 6 all over 6 we get 3.5, 21/6. Just like before, we did get the right answer. But this theorem works in general, no matter what your random variable is. How is this theorem proved? Well, I will tell you, to tell you the truth, the book doesn't really prove it. We will look at it after our break here. It doesn't really prove it because it's doing a little hand wavy stuff. That's what Dr. Wetzel would call verification instead of proof. Let's go ahead and look at what the book calls a proof of this. Here it is as a theorem. Let mx of t be the moment generating function for the random variable x. Then yes, this says the kth derivative with respect to t of the moment generating function evaluated at t equals 0 equals the kth moment of x. Realize that these things are numbers for a given random variable and a given positive integer value of k. The expected value of x to the k power, the kth moment, is a number. And yes, that derivative evaluated at 0 is a number. How is this quote unquote proved? I said it's kind of hand wavy. To prove this theorem, let z equal e to the tx and use the Maclaurin or Taylor series expansion for e to the tx. Which you should remember from Calc 2. What isn't it called, the Taylor series? Oh, it's Taylor series centered at 0, or sometimes called Maclaurin series 2. If it's not centered at 0, then you call it a Taylor series for sure. But anyway, this is the Taylor series for e to the z centered at 0. I hope you remember that from Calc 2 with those factorials there. Yes, replace the z's with t times x. That's the first hand wavy thing. What? An infinite series of random variables? Does that even make sense? Here's the second hand wavy thing. Take its expected value and assume you can pull the e through term by term. Extend the linearity of the expected value operator to an infinite sum. That's another hand wavy thing. This is not really a true proof in the full rigorous mathematical sense of the word. It's a verification, or it's a reason. You have to prove that this makes sense and can be done with infinite sums of random variables. We don't want to go there, right? We've got other things to do. We're just trusting. Differentiating with respect to t, can you do that on both sides as well? I mean, the series has got to converge, and I mean, this series is an ordinary series from Calc 2, because remember, those e's are a bunch of numbers. This is an ordinary power series from Calc 2, and it's going to have, if you remember from Calc 2, a certain radius of convergence, an interval of convergence, and certainly there are proofs in real analysis that can be used to prove that you can differentiate power series term by term within the interval of convergence. Bad memories from Calc 2? You didn't prove all that stuff in Calc 2. You were just doing calculations, like find the interval of convergence, like you had to use the ratio test and things like that. In real analysis, or at least more advanced real analysis than you may even get here as an undergrad, you'd want to prove that you can differentiate such a power series term by term within its interval of convergence. Anyway, they're just assuming you can do so. Differentiate with respect to t. Derivative of 1 is 0. Derivative of t times e to the x with respect to t is e of x. Did I say e to the x? E of x. It's just a number. Derivative of t squared over 2 factorial equals 2, times this number is, bring down the power of 2, 2 divided by 2 is 1. That number, e of x squared, times t to the first. Yeah, the derivative of that is that. The derivative of that is that. Plug in t equals 0, you'll get the first moment, the mean. Magic. Next page. When the derivative, yeah, okay, they say plug in t equals 0 there. Take the second derivative. Get this, plug in t equals 0, get that, the second moment. It can be continued, if you want to be extra picky, maybe by induction, that for an arbitrary positive integer value of k, this is going to be true. You get the kth moment. So the first moment is the mean. The second moment is not the variance. Oh, that brings up a word of warning. It's very common for people to actually accidentally think the variance equals the second moment. Like these two things are equal. No. Not equal. The variance is the difference, not just the first thing. The variance doesn't equal the second moment, but you can use the second moment to find the variance. By the way, if you happen to know the variance and the mean, you could also use this equation to solve for the second moment. You could add the square of the mean to both sides. That's something else you can do with this equation. That I don't think I ever asked you a question like that, but I have seen it come up on actuarial exam problems. Okay. So what's a moment generating function good for? It's good for generating moments. It's also good for something else, maybe even more important, you might say, in chapter 7. Chapter 7 might be my favorite chapter. For identifying random variables. Usually you got a random variable, you can find the moment generating function. Sometimes you got a moment generating function, you want to figure out what the random variable is. That actually has super important applications in statistics. I'm thinking of a theorem in chapter 7. Perhaps my favorite theorem of the course. I don't know, there's a bunch to pick from. This one right there. Let x and y be random variables with equal moment generating functions for all t in some open interval around 0. Then x and y have the same distribution, meaning they're essentially the same random variable. One subtlety here, just because two random variables, x and y, have the same distribution, doesn't mean when you actually observe their values in the random experiments that they will be the same values. They have the same distribution means they have the same probability mass function in the discrete case, probability density function in the continuous case. They have the same CDF, they have the same mean, they have the same variance, they have the same standard deviation, etc. Which reminds me, I forgot to find the standard deviation for our dice example. What was the mean? The mean was 3.5. Yeah. Oh no, okay, the mean was 3.5. The variance was 2.916 repeating. Yes, the standard deviation is the square root of the variance, about 1.7. I've been hinting that the standard deviation is easier to interpret. Here's one way it's easier to interpret. Almost all the probability of a distribution is going to be within 2 standard deviations of the mean. It's called a rule of thumb. It's not a very precise statement. It's just hand wavy, approximately true statement. It's good enough for most applications. Almost all the probability, or with statistics, almost all the data, is within 2 standard deviations of the mean. So if the mean is 3.5 and the standard deviation is 1.7, 2 standard deviations would be 3.4. Almost all the probability for our example will be within a distance of 3.4 of 3.5. There's 3.5. 3.4 units to the right would be almost to 7. 3.4 units to the left would be almost to 0. Yeah, 100% of the probability. The values that give you positive probabilities in this case are within 2 standard deviations of the mean. It's not even an almost in this example. It is 100% of the random variables values that get taken on with positive probability are within 2 standard deviations of the mean. That rule of thumb applies, though, for any random variable. But the word almost is kind of vague.